Welcome again, everyone. Last lecture, we talked about permutations, and now we want to talk about partial permutations. These are permutations where you don't want to arrange all the objects that you have, but just some subset. Okay. So we know that the number of ways to arrange n objects is n factorial, and we would like to determine how many ways or in how many orders can you arrange some of the n objects. Okay. So for example, let's look at pins that consist of 2 digits. So if you allow any digits, then for example 11 or 45, in other words you allow things to repeat, then the total number of pins that you have is 10 times 10, 10 for the first choice and 10 for the second choice, or it's 10 times 10, which is 100. Okay. On the other hand, if you insist on the digits being distinct, then for example you allow 0, 5 and 3, 2, but not 3, 3 because 3 repeats, then you have 10 options for the first digit and 9 options for the second digit, and the total number of ways you can do it is 10 times 9, which is 90. Okay. Similarly, if you look at 3-letter words, then if you allow any letters, for example MOM or XYZ, so for example here we see repetition, then you have 26 for each letters, or 26 cube is the total number of 3-letter words that you can come up with. But if you insist on distinct letters, then and you allow things like ABC but not dead, then the number of different sequences you can have is you have 26 options for the first letter, and then 25 for the second, 24 for the third. So you just get this product. And as you can see, it's just the calculation that we did for permutations, except that we're not going all the way down to 1, but we're just finding just 3 out of this 26 elements. In other words, what we're counting here is we're saying we have 26 elements, as in this case, for example, the 26 letters, and we don't want to arrange all of them, but we want to arrange 3 of them. And the question is, how many ways can you do it? And another way to view this thing in a completely identical way is to say that we are looking, instead of sequences where we allow all possible sequences, this would give us the Cartesian product. Now we're looking at sequences where we insist on that all the elements are distinct. Okay, so that's another view of the same problem. Okay, so how many partial permutations are there? We call such permutations where you have n objects and you want to arrange k of them. We call it a permutation of k out of n objects, or we call it a k permutation of n. And we want to calculate how many such k permutations of n there are. So as we just said, there are n ways to write the first element, and then n minus 1 to select the second element, and so on until we get to n minus k plus 1 to select the kth element, right? Because it's n for the first one and n minus 1 for the second, so it's going to be n minus k minus 1, or n minus k plus 1 for the kth element. And this number, we can easily see that we can write we can continue it up to, if you want, times n minus k all the way times 1, and then divide by the same thing. So we get that this is n factorial divided by n minus k factorial. And we denote this by n to the k with an underline. We call it the kth falling power of n, and some people denote it by p and k for permutation of n elements, where we take just k of them. Okay. So here are some values of the kth falling power of n for small values of k. So for k equals 1, n to the 1 falling power is just n. For k equals 2, it's n times n minus 1. For k equal to 3 is n times n minus 1 times n minus 2, and so on, up to for k, it's n times n minus 1 times n minus k plus 1, as we define it to be. So let's finish with an example of partial permutations. So imagine that you have 5 programming books, 5 probability books, and 6 machine learning books. And you wonder, how many ways can you write a list that contains 2 books from each subject, where books from the same subject are listed consecutively, namely next to each other. So we wonder how many such sequences there are. And examples of lists like that would be the 3rd probability book, the 1st probability book, and then the 5th machine learning book, and the 2nd machine learning book, and programming book number 1 and programming book number 4. We can see that the probability books are listed together, the machine learning books are listed together, and the programming books are listed together. Or machine learning 2 and machine learning 6, followed by programming 1, programming 2, and so on. Again, all the books from the same topic are listed next to each other. So we wonder how many such sequences there are. So we're going to use a combination of factorials and permutations, and in some sense we're using the product rule many times. So we'll show that the answer is 3 factorial times 4 to the second falling power times 5 to the second falling power times 6 to the second falling power. To see that, notice that we can first decide on the order of the topics. For example, here, machine learning, programming, and then probability. So there are 3 different topics, and the number of ways to arrange them is therefore 3 factorial to decide on the order of the subjects, like here, machine learning, programming, and probability. And then once we do that, we need to decide which machine learning book we're going to choose first and which one we're going to choose second. And because there are 6 machine learning books, which programming book we're going to put first and which programming book we're going to put second. And because there are 4 programming books, then we have 4 to the second falling power number of ways to do that, because we can decide on the first programming book and then the second programming book, and then we can decide on which probability books we're going to choose. And since there are 5 of them, we have 5 to the second falling power, or 5 times 4 ways of doing that. And then we need to decide which machine learning books we're listing and in what order. And we have 6 ways to choose the first one and 5 to do the second one. Or in other words, we have 6 to the second falling power to do that. And we take the product of all these by the product rules, because we're making a decision of the order and we're making a separate decision for which programming books we choose, which probability books we choose, and so on. So we take the product, we get the total number of ways of creating such lists. So we have talked about permutations and we've talked about partial permutations, and next time we'll talk about combinations. See you then.